Good morning, everyone. Thank you for joining Teledyne ISCO's October webinar focusing on peptide purification. Today's webinar will be led by Jack Silver, Teledyne ISCO's application specialist. If you have any questions or comments throughout the webinar, please utilize the chat function within the Zoom platform. This webinar is being recorded and will be available for all attendees after the webinar today. At this time, I will turn it over to Jack to get started.
Okay, good morning, and thank you for your time, and thank you for joining us today. We're going to talk about peptide purification, and our agenda is going to discuss the advantages of mass-directed purification. We're going to discuss the pre-purification of peptides using flash chromatography. We'll also talk about the effects of pore size on the stationary phase and how it affects the purification of peptides. Likewise, we will discuss the effects of the chain length on the reverse phase and how that affects peptide purification. So why would you want to purify peptides? Namely, to save time and money, or if you have some peptide that you used for a project and you need it again, you find it decomposed a little bit, you could polish it up and get it very pure again. We have some peptides that we purchased from a vendor, and you can get crude peptide in a week and it'll cost about $2,000, but to get pure peptide, it will cost on the order of about 3 to 4 weeks of your time, and it will cost a little bit more as well. So we'll start with mass-directed fractionation. And why would you want to use a mass spectrometer for a detector? This example is the synthesis of benzene, and although it is not a peptide, it demonstrates the positive identification very well. This is a synthesis I had done, and unfortunately, I was a little slow in the workup, and the benzidine rearranged and oxidized the azobenzene. The desired compound was the minor peak that alluded a little later, the second peak, and I only had 6 milligrams. The major component, the azobenzene, was 60 milligrams. However, the collection of the correct peak saves time. You don't do research on the wrong compound and wonder why you're not seeing activity, or the activity is not what you expect it to be. Due to synthesis solutions, peptides are very often complex mixtures. Peptides are collected by UV detection. However, with the mass spectrometer, you can be very specific in what you collect, and you can get the compound that you want to be more pure because you're able to cut it better from the impurities. The other reason for using a mass spectrometer is simply to save time and solvent, because it can be a very specific detector for the compound that you want. You can end the run after your peptide dilutes. Our software has a feature called Terminate on Target, which pauses the run when the desired masses are observed, and it allows the user to go directly into the column wash or do another run if they need to. We're going to talk about a few definitions here. Some of you people who might be familiar with mass spectroscopy, bear with me for about 2 slides. M is the mass of a given molecule. That's the uncharged molecule. The base peak is the tallest peak in a mass spectrum, and provided it is a peak related to your compound, you will get the most sensitivity if you do mass-directed purification using the base peak. M plus H is the mass of a molecule with a proton, and in this case, it would carry a positive charge. Likewise, M minus H is the mass of a molecule that lost a proton, such as an acid. It would carry a negative charge. It's possible to multiply charge a molecule. We'll discuss that a little bit further, but you can have M plus 2H, which would then be doubly charged. Some more definitions. The nominal mass is the integer mass using the most abundant isotopes, and it's the number we usually state in conversation. The caffeine that we have over here has a formula weight of 194.19, but we would say it has a mass of 194. The monoisotopic mass is the sum of the atomic masses using the most common isotope of each element in a molecule. The exact mass is used by some chemistry software such as ChemDrawer. It's the sum of the atomic masses of the most common isotope if you don't specify any isotopic species. If you do add some isotopes to it, that's done with peptides, the exact mass would then change to be the mass of your peptide with the isotope in it, and the other parts of the molecule would simply be the most common isotope. In this case over here, that causes the difference between monoisotopic mass. The average mass is the sum of the average atomic masses in a molecule, and that's the number that we use when we talk about when you do yield calculations in a synthesis. It's the number that you would see written on the bottle of reagent from your favorite chemical supply house. So over here, for caffeine, the monoisotopic mass and the average mass are close enough to one another that for modest resolution mass spectroscopy, they're considered about the same. 194.08, 194.2. A single quadrupole would pick up either of those without too much difficulty. For peptides, I tend to use the average mass. Over here, the sequence that we have listed is a fairly small peptide. Its monoisotopic mass is 1091.5, but its average mass is 192.5. And that's enough difference to miss detection in extracted ion detection. Peptides, even small ones like this, they have enough atoms in it that you're starting to see the natural abundance. You start to see the average show up in every molecule. I tend to use about 800 grams per mole, where I start using the average mass instead of the monoisotopic mass for peptides. And larger peptides will show a greater difference between the monoisotopic and the average mass. And we'll show you that in a couple of slides. One last page of definitions is XIC and TIC. XIC is the extracted ion current, which we usually use for peptides. It's the ion current for a limited mass range, usually a mass to charge ratio, or M/Z of 1 or 2. And we use it to monitor characterized compounds. The total ion current, TIC, uses the entire spectral range. It's useful for natural products or other unknown compounds. It's also useful for molecules that generate a weak molecular ion peak or tend to fragment. Sometimes you can do the detection by looking at the fragments of the molecule rather than the charged species that isn't in pieces. So mass spectral evaluation is used to verify the peptide. On our systems, we have MS method development that allows you to do an injection and verify that you see the compound that you're interested in purifying. It lets you also adjust the settings and choose the best ion settings. An example here is thymosin. Its molecular weight is 3,066 grams per mole. Our mass spectrometer only goes up to about 2,000 Daltons, but the thymosin has a mass of 3,066, and I can detect it by using multiply charged species here. So over here, I have the M+2H of 1533, an M+3H of 1023, and finally an M+4H of 767. You will also notice that the M+3H is the base peak here, and I would use that for detection as it improves the sensitivity of my mass spectrometer. It's important to note that these are not fragments. The peptide is larger than what can be directly detected on the pure ion L. I will show you that the presence of the multiply charged ion simultaneously in a peak is unambiguous proof of a compound. And multiply charged species shows why we scale by Daltons mass to charge rather than simply mass on a mass spectrometer. In this case, the M+3H, the base peak, has a M over Z of 1023, but that's obviously not its mass. How do we get these multiply charged peptides? They're charged by basic residues such as lysine, arginine, and histidine. Some other residues can also take a positive charge, but these basic groups, these amines on it, do a nice job of holding onto a proton. Occasionally, one of the amide linkages in the peptide will pick up a proton as well. And you can show whether a peak is a fragment or part of your peptide by this equation. The mass to charge ratio of that peak has to fit this equation where it's mass plus however many protons, Z protons, divided by Z. And if it fits that equation, there's a good chance that that peak is from your peptide as a multiply charged species. One question that you might ask is how many charges can a peptide take? Obviously, it depends on the length of a peptide. Larger peptides can carry more charges on them, obviously. It depends on the number of residues that can hold a charge. And also, there's a coulombic interaction. Like charges try to stay away from each other. And so for that reason, it was determined by the reference listed at the bottom over here that you need at least 3 residues between charges. You can't charge a peptide, on the next residue over or 2 residues over. You need 3 amino acids between charges. Another evaluation example is a customer sample AS48 whose sequence is over here. Its molecular weight is 7,787 grams per mole, and the pure ion, as I mentioned, has a limit of 2,000 Daltons. Can we see this? Well, the answer is yes, we actually see it pretty well. What we see is the M+5H, the M+6H. We see the M+7, M+8, and even the M+9H is visible. It makes a fairly unique pattern, and the M+8H is the most abundant ion, and so it forms the base peak at 975 Daltons. What you are looking at is the crude peptide before purification, but even so, we could still see it. We talk about flash pre-purification now, and we will also apply the mass-directed fractionation to flash chromatography. Again, I'm going to step away from peptides for a few minutes and talk about how you dissolve your sample and how that plays a role in the purification of your peptides. If you dissolve your sample in a strong solution, like maybe mobile phase, or alternatively DMSO is stronger than water, what you might see is the compound in a flash column, it goes down the column and streaks down the column. And you can see that in the chromatogram where the peak is fronting a little bit. At about 1 column volume, or about the void volume, you see a small peak over there. That's actually some of the compound that got washed down with the injection solvent. Okay, even though this is flash chromatography, the exact same things happens inside a steel prep column, as I will show you in the next slide. But if I can dissolve the sample in water over here, at the same time in the purification, about 1 void volume into the purification, this column still looks nice and clean, and it was the same column used. A little later in the purification, you see a very nice band shape for the compound, and that's reflected in the chromatogram where I have a very symmetrical peak. There's nothing eluting at the void, so you can see that the compound was not washed out. Same thing in preparative chromatography. In this example over here, I have a couple of compounds that I dissolved in DMSO. And so what we see at the front over here is the eluting at about 2 minutes is the DMSO. And then at about 4.5 minutes, you see the first peak and the second peak at 6 minutes. This is a pretty good purification that we have over here, where the peaks are well resolved at baseline, and that would be an acceptable purification. However, I still have a lot of resolution at baseline, so I tried to inject more sample. I injected 2.5 mils, and we see now that I no longer have good clean chromatography. The peaks are running together somewhat over here, and the peaks are also running into the DMSO at the front of the purification. Next slide. The first, on the upper left, the chromatography was carried over from the last slide. The upper right shows the same purification, except I dissolved the sample at the same concentration in 2.5 mils of water. You see that I have greatly improved peak shape. I have baseline resolution. The peaks have a short spin shape that's fairly typical of an overloaded column. However, we're not doing analytical chromatography, and so that's a perfectly acceptable purification. In preparative chromatography, it's important that we get baseline resolution. Down at the bottom over here, I have the same sample, except I injected 4 mils of it. I still have baseline resolution. So I'm able to inject and run 4 times as much sample as I could when I injected the sample in DMSO. When working with DMSO, we do that because it's very convenient. DMF also does the same thing as DMSO. And when using DMSO and DMF, it's the very polar compounds that are affected more by the polarity or the lack of polarity, the solvent strength of the DMSO or DMF. Unfortunately, that's where a lot of our peptides tend to elude. An awful lot of them tend to be fairly polar compounds. So how does this affect peptides over here? Well, over here we have a peptide that needed to be cleaned up. We see that with the mass spec, we have a peak, and then we have some non-polar compounds that are eluting. So now I go and run the peptide on the prep system. I have my DMSO peak. I could load 13 milligrams, and I see that I have some impurities, and I just about can get baseline resolution with 13 milligrams loaded, and I could recover 8 milligrams of the compound. I need to do a column wash over here because, as you can see, there's some material that came out very late. And so that has to be washed out, otherwise it could form ghost peaks on the next run, or it can interfere with the next run. That non-soluble material also made the sample not soluble in water, so I had to use DMSO to dissolve everything. The mass spectrometer, the blue trace does show that the compound eluted, but 13 milligrams isn't a particularly heavy load for a prep column. This was a 20 millimeter by 150 millimeter column. So the advantages of flash prior to prep is that the flash column acts as a pre-column. So if there's anything that will get stuck on the column or otherwise potentially damage the column, you can use a flash column, and that's a lot cheaper than the steel columns. You have the possibility of different chemistries and selectivities, and that makes it easier to remove some of the impurities. By removing impurities, you increase the concentration of the desired compound relative to the impurities. And when I showed you the previous run with the 2 peaks dissolved in the DMSO, you want to minimize the use of DMSO if possible, and so you want to increase the concentration of what you want to purify, so you inject as little DMSO as possible. And the preparative column injection is limited by solubility, so that's one reason we use DMSO. The sample loop size as well. You can dissolve your sample in a weaker solvent, and that is better, but if you only have a 5 ml loop, that limits you to fairly small injections. By removing the nonpolar impurities, it just becomes easier to dissolve the sample. So let's look at a flash purification run on a ReadySep Gold RF C18 column. Over here, I have the purification. The square indicates where I collected the sample. The green indicates one peak, and the purple shows another peak at the bottom of the chromatogram. And the big oval shows the nonpolar compounds that we are removing. I dissolved the sample in DMSO. I loaded 100 milligrams, and I collected 40 milligrams from the red box. And that very roughly corresponds to what we saw with the prep HPLC, where I got roughly half of the material back after purification. But now, after I got done with the flash chromatography, let's take a look over here what we get. I was able to dissolve the sample in water because I got rid of all of the non-polar materials. I was also able to load 30 milligrams. You might recall that previously I could only run about 13 milligrams. And note that I got 23 milligrams of the desired compound. I could actually have loaded more because you can see that I have baseline resolution between the desired peptide shown with the mass spec that I collected it and with the blue trace. So that's very good. The other nice thing is after about 8 minutes, I could have stopped to run. And because I don't have anything else I need to wash off the column, I could start another run immediately if I needed to. Because I ran such a flat focus gradient, the equilibration would not take very long, so I drastically increased my throughput. I get 3 times the loading in a single run compared to the original purification. The ability to dissolve in water allowed a higher loading, and I could end the run, and I could start another run, so that's 2 runs within the same time as I could do before. So that's potentially 6 times the throughput that you can do by doing a single flash pre-purification. And that flash pre-purification takes the same time as one of these prep LC runs. After purification, here's my analytical HPLC. Both UV and mass spec line up, and there's nothing else in there. The peptide is nicely purified. The next thing we will talk about are the effects of pore size on peptide purification. We're going to start off with small molecules and use that as a baseline for what's happening with peptides. I have a column over here which I had 120 angstrom, 200 angstrom, and 300 angstrom pore sizes. The compounds were methyl, ethyl, propyl, and butylparaben. And looking at the top at 120 angstrom, the first peak elutes at 6.96 minutes. 200 angstrom, it comes out a little earlier, and 300 angstrom, it comes out at about 5.6 minutes. All of the peaks elute a little bit earlier. So the question is, why might that be? Well, the larger pores are obviously causing reduced retention. That's really because of reduced surface area, and that means with less surface area, there's reduced interaction with the stationary phase. And with 5 angstrom, with small pores, you can see you can have a lot more surface area compared to large pores. What about peptides? So what we run over here are EGFR at 1,635 grams per mole, thymosin at about double the molecular weight, and our friend AS48, where the molecular weight is doubled once again. And these peptides will be used for the rest of the presentation. So over here, you can look at it as peptide size going from small to large, pore size going from small to large also. And so what we see over here is the EGFR with the 120 angstrom pore elutes at 4.22 minutes. 200 angstrom pores elutes at 4.19 minutes. And the 300 angstrom pore, it elutes at 4.1 minutes, 4.11 minutes. And so you would say to me, well, so what? That's exactly what you just showed us with the parabens. You increase the pore size, the compound elutes later. Now let's look at some other peptides over here. The thymosin elutes at 4.368 minutes. 200 angstrom pore, it elutes at 4.44 minutes. And the 300 angstrom pore elutes at 4.65 minutes. The AS48 with the 120 angstrom pore elutes at 8.95 minutes. 9.21 minutes for the 200 angstrom pores, and about 9.2 minutes with the 300 angstrom pores. With these peptides, it's behaving a little differently than the small molecules or from the EGFR. The peptides are actually eluting later. That suggests that having larger pores allows better interaction for the peptides with the stationary phase and allows potentially better purification. So why does that happen? I'll introduce the concept of an effective pore size. Large molecules don't fit into the large pores. The stationary pore inside the pores is inaccessible to the peptide, and that means the effective surface area is reduced. When I say effective surface area, that is the surface area that is available to come in contact with your molecule and is useful for purification. Pores that are too small, that part of the column might not exist as far as the peptide is concerned, simply because the peptide can't interact with it. The large peptides can fit into the larger pores, so the effective surface area is increased, which leads to better retention, as you can see from the cartoon here on the right. The changeover from small molecule to large molecule in this context is about 2,000 Daltons, as you saw from the previous slide. So now we will investigate the functions of chain length on peptide purification. So we're back to our small molecules again. And as I go from C18 to C8 to C4, it's pretty clear that the molecules come out a little bit earlier here. They don't retain quite so well with small reverse phase change. Again, let's look what happens with peptides. We're using 200 angstrom pores over here and going from small to large peptides, and we're going C18, C8, and C4 at the bottom. And what we see for all of the peptides, EGFR, you see 4.19 minute elution. C8, you see 4.24 minutes, and 200 angstrom is 4.27 minutes. Thymosin, you see the same trend, 4.4 minutes, 4.73, and 4.8 minutes as we go to the smaller chain. AS48, 9.2 minutes, 9.29, and 9.72 minutes with the small chain. So for all of these peptides that have different chain lengths, you can see that they have somewhat different polarities as well. The AS48 does elute much later in the gradient than do the other peptides. It's a little less polar. But for all of them, the shorter chain length causes better retention. Why does this happen? The reason for this is the pore size increases as the chain length decreases. So we look at a pore here on a C18 column, and the green represents the area that's accessible to the peptide. We go to a C8 and we open up that pore considerably. And then for C4, that pore gets opened up even more. So as we shorten the chain length, we make the pores larger and we create a higher effective surface area. In addition, there's a change of adsorption mechanism with peptides compared to small molecules. Small molecules can sit in between the C18 chains and they can interact very nicely with the C18. Peptides, on the other hand, are too large to go in between the C18, but they have to sit on top of the C18. As a result of that, the effective chain that the peptide sees is only at the very tip of that C18, up near the top over here. As you shorten the chain length, the chain can't bend, and it interacts better with the peptides. So the peptides have better retention with the smaller alkyl chains. There might be another interaction as well. With the chains getting smaller and shorter, that brings the peptide closer to the silica surface, and that could potentially allow interaction of some of the polar portions of the peptide with the underlying silica. So there might be two mechanisms that we're starting to see as well. So the conclusion is time and money savings are possible with purifying peptides. Certainly time. You can purify the peptide yourself and get it very pure within the course of one day instead of waiting a month to get very pure peptide. Mass-directed purification is useful for collecting the desired compound with improved purity. Even a modest mass spectrometer, a single quad system such as the Pure Ion, is capable of detecting rather large peptides, and those are best detected using the average mass. Flash chromatography is very effective for pre-purification because it removes the impurities that make dissolution more difficult. It increases the concentration of the desired compound and allows a higher loading, which in turn allows increased throughput. Peptides elute differently compared to small molecules, leading to better results from wider pore columns and often better results from shorter chains. So we see that perhaps a C4 or C8 might work a little bit better. And we seem to believe that 200 angstrom seems to be a sweet spot for peptides. When you run a bunch of them, it seems like 200 angstrom pore sizes seems to be a good combination of effective surface area for large and small peptides. At this point, I will open it up to questions, and that should show up on a screen over here. Any questions? If there are questions, perhaps someone over at Lincoln can read them out to me.
Hi, Jack. We had one question come in so far. It is, what do we need to do with cyclic peptides in terms of what C18 column size pore needed to be used?
Okay, cyclic peptides are kind of fun. I'll give a little hint. I used to work with those. I found out when I worked with antifungals that some cyclic peptides are effective. They seem to punch holes in cell walls. And one trick that you might try is aluminum oxide, of all things, for a flash column. And that does a decent job of cleaning them up. Also for pore sizes, I would tend also to use the 200 angstrom pore size. The same effects happen with a cyclic peptide as you would see for a straight chain peptide. They are somewhat larger molecules, although with their ends tied together, they're constrained in some of their movement. But those peptides, in order to make a chain, they also tend to be larger molecules with a molecular weight of very often over 1,000.
Okay, we'll give it a minute or more. So if you have questions, feel free to use the chat function, or there is a Q&A function that you can put your question in, and we can go ahead and get those answered. Another question that came in, a follow-up to the question you just answered, Jack, is you said in your presentation to use aluminum oxide for cyclic peptide?
That was one thing that I had some good luck with. At the time, I was collecting the cyclic peptides from bacterial fermentation, and they showed up as antifungal. And the purification procedure that we used involved absorbing on the polymeric reverse phase as a first step, and then aluminum oxide got that particular peptide very nearly clean. So we were working with some pretty dirty material. So if you're working with a synthesized cyclic peptide, that's one issue that you don't have to deal with. It's removing all of the fermentation byproducts. But even so, aluminum oxide is a pretty good way of resolving a peptide from, say, non-polar impurities. We have aluminum neutral columns that you can run on a flash system, and you can evaluate it first on a very small column and see how well it works.
Okay, another question we have that came in. Have you worked with low charge or essentially non-polar peptides, and what are your recommendations?
Okay, low charge or non-polar peptides in some sense is a little bit easier. The DMSO doesn't affect non-polar peptides anywhere to the extent as they do the peptides that we were describing in this webinar. So I'd be okay with dissolving those in DMSO and running it. But even so, a flash pre-purification could be helpful because one can then use a fairly flat gradient and not have to worry about washing out stuff at the end.
Okay, and while we give it just a few more minutes for questions, just a reminder that this webinar is being recorded and will be available to all attendees later on this week. We'll give it a minute or so more, and then if you do have any follow-up questions after the webinar, Jack's contact information is on the screen right now, and he would be available for further conversation as well. Here is another question that's come through. Flash chromatography, can it be used for large quantity cyclic peptide purification, or is it just a cleanup before prep?
It can be used for large cyclic peptide purification. In fact, the aluminum oxide that I had used was packed in a flash column when I was doing that work. Also, another thing to note is that you can use like a water methanol or water acetonitrile on aluminum oxide as well.
Great. Okay. Well, thank you so much to everyone for joining us today, and thank you to Jack for walking through this presentation for everyone. Again, if you do have any follow-up questions, Jack's contact information is on the screen currently. We appreciate everyone's time and attention, and have a great day.